So, Jelmer, are we back? Okay, welcome back everyone. A kind word from our sponsors, because Innovation Lab is paying for the drinks and the food. So a warm hand for Andres from the Innovation Lab. That's said and done. So now for the next speaker, Sami, you're with the ACE team, with the Analytics Competence Center. And the topic modeling, is that what you're working on a day-to-day basis?
No, actually, topic modeling is something that I did last year, and now they're live, so I'm working on other stuff, but I'm going to explain about what is currently live.
Okay, cool. Good luck.
Yeah, so this is something, the topic model is work, topic modeling is work that I did last fall. And it's basically, the idea is to get a bunch of articles and automatically cluster them to different topics based on the words that they contain. So there's no external knowledge and there's no human involvement. It's just automatically clustering them to topics. And this was then later used for deciding or predicting the interests profile for online users, and also to do the demographics predictions. So this is it's an article processing step. So this there are two major points to it. First, you get in the text, which is natural text in a digital form, and then you have to process it to be able to do some modeling on it. And then first I'm going to explain about this processing, and then about the topic modeling. So in the beginning we have an article, which we first split into words. Then we remove anything that doesn't actually appear to be a word, like these dashes and numbers. We can't actually decide anything about. They don't express themselves anything about the content or the topics of these articles. So we just remove them. And then let us focus on this one word. It's in Finnish, pyysi. And look at how we have to normalize it in a sense. This is not in its original form, pyysi, which is to ask in Finnish. It's changed in the context of that sentence, but we want to match words between articles, so we have to somehow normalize it. There are two ways to do that. First is stemming, to remove anything added in the end, and to get like the basic form or the base form of that word. That is quite much used in search engines, at least in the past. But then there's also the possibility to go even a step further and take the original form called lemma, which is to if you go to a dictionary and look at the word up, that's in the form. It's in the lemma form in that dictionary. So in here, I will later show you examples in different languages. But in here, the first row contains the originals in the context of the sentence, these articles, or these words. And the second row, you have the stem, which is just you remove something from the end to contain the stem of that word. But as you can see, the stems don't match in all these three examples. The leftmost example is different from the rightmost sample is different from the other two, even though they come from the same, they basically are the same form, the same word. But if we take the lemma, we arrive at the same word. So this is a pre-processing step for the text to make the words such that it doesn't matter which sentence they are used in, but it only matters what they represent. And so we can match these same words in other articles. In English, these examples would look like this. So the first row would be the break. It's in the original form. The second example, you can see that when we take the stem, the first and second match, but the third doesn't match in the stem. So taking a lemma makes all of these words match. And in Dutch, the same. So again, back to the article where we've removed all the dashes and numbers. Now we convert all of these words to their lemma form. It doesn't make any sense reading that. It's not a natural language anymore, but it contains all the words in lemma form, so we're able to match articles between articles. And now there are some stop words. They're called stop words because they are so common that they appear in multitude of articles, but they express no information about the actual content. If you take this word, you really can't say what topic it is. For instance, take word football. That tells a lot about, it's not about economics, it's not about science, it's football. But if you take the word ask, it doesn't say it's football or economics or science, it's ask, it's just a word. It doesn't tell us anything about the topic. So we identify these stop words, and they come from a list. And we just remove them and then end up with a representation called a bag of words. So this is just all the words in the article processed and combined to a collection of words.
Can you go to the previous slide, because I need to ask.
Nope, sorry. This is one way. I can, if you can make the question.
Sunday, or I mean, is that telling something relevant for the
Sunday.
Sunday?
Yeah, the question was there was a stop word called Sunday, which I marked as a stop word. A stop word list is an interpretation of what is and is not a relevant word. I had that in my stop word list, but you can always argue if that's relevant. I would say in this context, when I was given, or I downloaded all the articles in Finnish papers that were published in digital form, everything that I got was available. I considered Sunday not to be relevant in the sense that we have like sports, we have economics, and these kinds. If you go into specifics, if you have only very narrow subjects, you might find it reasonable to have. Let's say some sports might happen only on Sundays, then it might be reasonable. But in my list, that was a stop word.
One more question. How did he identify this list of stop words?
I downloaded it from Google. Okay, so now we have a bunch of articles that are processed in this way. And then we go into topic modeling. So now we have our articles on the top, and I've chosen to divide them into 3 topics. Whoa, it goes back. So I'm going to explain quite technically how this algorithm works. So first, we take the first article and randomly assign them. I've actually randomly assigned all the words to topics, and the algorithm then tries to change the topics of each article to somehow cipher which articles belong into same cluster, which to the same, which to the first, which to the second, which to the third. So in here, you can see on the bottom are the words in this current article and their topic assignments. Then these graphs on the top, or the bars there, represent how many words of that kind are in each article. Let's take Barcelona, for instance, here, which is almost at the top. In the first topic, there are a lot of articles had word Barcelona, and that was assigned to topic 1, just by random. And the other 2 topics don't have that word that much. So now let's focus on this word Barcelona, which we want to sample. We want to assign it to a topic that we think it goes to. It should go to. So let's first look at the in each topic, look at the counts of this word in that topic, and also look for this article on the with the number of words. Well, actually, I'll explain this. So the number of words expresses how many words in that article belong into that topic or have been assigned. So the word Barcelona will be assigned to a different topic based on these numbers, and these numbers are combined to become probabilities. So now on the bottom you can see probability, and that expresses how likely we think this word to, what is the probability that we think this word belongs to the topic 1, topic 2, and topic 3, respectively. And then we sample, or actually this is the part where we actually calculate the probabilities. Now, previously we just combined the numbers and then sample, and we see that the probability for the first topic was so big that that prevails, and we assign this word to the first topic. Then we move on.
Is there a question? How come you are looking at individual words and not in any context? I mean,
The context comes from these numbers. If you look at the number of words, it tells me, you can see it as weight, how many words, for this article, how many words are in one topic. So how much of that topic is represented in this article. That's context for the article. And the other context is the number of words in each topic. So if we go look at the Barcelona, the context for Barcelona in topic 1 is that topic 1 had a lot of words of Barcelona, but the other topics had very little. The contexts, these two contexts, article and topic, are combined to the probability, and then we assign or sample. We randomize to assign the word to a topic based on that probability. And we can see that we do the same over and over again. Actually, what we can do is speed it up. And when we've done with one article, we move to the next and move to the next. I'll just reduce the speed a bit. So what this does is it goes through these iterations, goes through all the articles several times, and because it's based on probability, there's a probabilistic model behind it. So in the end, when we've done sufficiently many iterations, we arrive at a topic assignment. So let's look at it in a iteration scale. So now on the left, you have the number of words for each article, the number of words in each topic. So the bigger the bar, the more words they are. So you can think of it as the weight of that topic in that article. And on the right is just for each topic the number of words in that topic. Now let's go and look at each iteration at a time. You can see that the number of words in each topic change, and also the number of words for each article, the number of words in each topic change. Let's just let it play. And it appears that there are all the articles are now assigned to 2 topics. There are actually 3 topics there and 3 different categories, but because I randomly put them somewhere in the beginning, it can happen that the topic assignment is not found if that is there. So what I will do next is start from scratch, and you can see that the articles have their words in 3 separate topics. And this is basically what the algorithm does. This I would call the optimal solution. I'll explain this first. I specifically selected 7 articles from 3 different topics. One is Lionel Messi, one is Edward Snowden, and one is avocado recipes. So they are highly separate, but they do have overlap in the words. If they don't, then this doesn't work that well. So they actually expect there to be overlap. Yes, there was a question.
You may have just answered my question. What's your training set?
The question was, what is my training set? There is no training set. This is a method that's based on completely in the data. So I do not have, you mean my data set? Training set is as giving the right answers. I don't have right answers. Yes, but that's. No, I don't actually assume that. But that's the model makes the assumption that there are only a few topics for each article. In production, we have 201 topics, which is very small, but for the purposes that we have now, it's sufficient. The plan is to increase that and make it more granular. There are like 26 topics about sports, combining all the articles between all, currently basically HS and Ilta-Sanomat. But there are a lot of other topics, and all the interest targeting capabilities are based on topic modeling of Sanoma content. I'm actually done.
First question from me. How did you build the presentation?
I coded it.
You coded it
in JavaScript, yes. So I implemented the method in JavaScript. Actually, it was online.
I used to be impressed with people doing the demo from Terminal, but this is as cool as doing that. So, any questions about the topic model?
So, did you have some initial list of the topics? Did you set it manually, or did it appear automatically?
The question was, did I have a previous or a given list of topics? And the answer is no. What this method is that you have the bag of words, so the articles with processed words. You just give them that, and the only parameter, or there are few parameters, like the biggest parameter is how many topics will you find, and the algorithm does it automatically, and there's no involvement from me. I'm not giving it any information to which topic each article should be or what topics to find. The result is, having found 200 or searched for 201 topics, is that there are like 12 noisy topics which contain not stop words, but close to it. And there was another question? The question is, where is this being used in production? In Finland, this is where all the Finnish articles are assigned topics based on a result of this article, of this method. And those are then used for the demographics prediction and interest prediction. And those are then used for ad targeting and also content recommendations later. Now they are actually live in ad targeting in Finland. And this is what we're actually currently doing for Netherlands articles with Arno Wester and our team.
What is the Finnish language library you are using to get the lemma?
So the question was, what is the Finnish language library that I'm using to get the lemmas from? I'm using Voikko, which is open.
Last question from Mika.
Was there?
Oh, actually, there was already a question about this. I was thinking, can you somehow apply this in our content library and use that for categorizing all the articles automatically?
The question was, can this be used in content library to categorize the articles automatically? And the answer is yes. The biggest problem and benefit is, your question is, do I give it topics? Because I don't give it topics, I get anything out. I have to interpret each and every one of those topics, what they are assigned to. It's not that I can get this result and just use it everywhere. There's a lot of steps to use it, but this could be actually in some places where we store content, this data is already there. So it is being used.